Thank you very much, and thank you for the invitation and the opportunity to speak today. So, yeah, today I'm going to talk about a little bit of the work that I've been doing in collaboration with Bernard and Claude in the last 2-3 years, focusing on N3LO correction in the singular limit, and also trying to go a little bit beyond that. So, okay, we don't need to motivate much. I would just like to set the stage. Of course, we're in a moment where we have a lot of extremely precise differential measurement coming from colliders. And although that's not the picture for all observables, for example, for Higgs physics, at the moment we're still not at a high level of accuracy from the experimental side. Things will dramatically improve with the statistics of the high-Lumi LXC. So getting a theoretical prediction at percent level accuracy is going to be key in order to exploit or make use of the huge amount of data that we're going to collect in the next decade. So of course there are many ways of going to percent level or like ingredients that are needed in order to go to percent level accuracy from the theory point of view in hadron collision prediction. One of the most naive one that we think about going to perturbative quantum field theory and think about the strong coupling constant being the largest of the small parameters that we have in a collider process. One of the most naive things is to just go to higher orders in perturbation theory in QCD. So one point that I think it's important to stress is that one naively think that alpha S at LXC energies is order 0.1. So if you want to get to percent level accuracy, probably N3LO should be enough. And N3LO should only give correction of the order of per mil. What it turns out is that that is not the case, and I think this was actually, kind of like understood and expected for very few cases, probably like Higgs production being one of the most prominent ones. But in the last few years, we started having inclusive prediction for QQ bar initiated processes like Dralian, where the N3LO correction were very, very small. So here I'm plotting these results, getting from the N3LO cross-section. This program has been released that calculates inclusive cross-section. And here this delta is basically the difference between one order and the order before. So delta sigma N3LO means what is the correction that you get on top of, for example, the N3LO by computing the N3LO. And of course, these predictions are known since basically the early 2000, and Kirill has been a huge contributor in that. And for Higgs, we are getting order 30% correction. So yes, you expect to get a few percent, you need N3LO. But for Dralian, that was not really the case. Like the correction in Dralian were very, very tiny, and so N3LO correction were expected to be very small. It turned out that not only they were not very small, they were like either the same order or even bigger than the N3LO ones, and actually they were outside of scale variation uncertainty bands. And this was then later understood in the fact that if we're looking at the correction channel by channel in Dralian, the correction were actually pretty sizable. There was just like some fine-tuning happening more or less for the energies relevant for on-shell production for the Z or for the W that made such that different channels were contributing with different signs, and so there was this fine-tuning giving a pretty small N3LO correction. This, of course, is not like a generic feature and was completely spoiled by the N3LO correction. And so even for processes where we were kind of expecting that N3LO was enough, we see that N3LO is probably necessary for percent level phenomenology. Now, of course, it's not going to be possible probably to do for all observable, but say that for what we can do, either the calculation of this correction or a very good quantitative estimate of them is going to be necessary if we want to push the phenomenology accuracy to percent level for LXC processes. So, of course, rather than computing very few observables at this level of accuracy, if we have to start doing that for a large variety of processes, the idea of like systematizing this very high order correction becomes of importance, primary importance. And we all know that for cross-section level calculations. So there is an issue in automatizing these kind of processes because you have to deal with IR singularities that kind of like come up analytically from the amplitude of the virtual correction, but they come out only after integration over phase space for the real correction. Of course, the complexity of these infrared singularities grow dramatically with loop order, and so it's not easy to systematize these order by order. So my approach today in this talk is try to use effective field theory methods, in particular soft and collinear effective theory, to study, as a matter of fact, soft and collinear radiation at the cross-section level. Try to, the FT kind of give you a way of systematizing the understanding of these limits of QCD, and we can try to leverage that to actually get, to push the level of accuracy that we can do for fixed order calculation at N3LO. So of course, the obvious application is to build the universal counterterms that contain the information about collinear and soft dynamics at the cross-section level. And one example of this is EFT-based subtraction, which is going to be a good chunk of the rest of my talk. And then also these fixed order terms in the singular limit are also a necessary ingredient to improve resummation, because these basically constitute the boundaries of a Riemann-Basic group equation. One needs to have them at a good, appropriate level of accuracy in perturbation theory, because then by running DRG, this gets hit by logs, and so not having these fixed order terms at correct order would not allow you to get very far in the resummation accuracy. So let me discuss EFT-based subtractions. These are a way to use some factorization theorems or EFT knowledge of the singular limit to try to generalize the fixed order calculation to higher order. So of course we have explained that to Massimiliano. It's a bit yeah, we can call them slicing methods. We can call it yeah, it's just that you need some kind of control coming from a factorization theorem, where you can call it in a different way. Yes, that is true. But in this talk, I'm gonna use EFTs to go to N3LO. So I don't know. Any way you name these methods, people get upset. If you call them slicing methods, people get upset. If you call them subtraction, then the subtraction people get upset. EFT-based subtraction correctly, people not using EFT get upset. So whatever. QT and injecting a subtraction. Well, I mean, the idea is that basically if you can come up with an observable that isolates the Born configuration of your process in the region where this observable is zero, then you can think about your cross-section as the cumulant of a differential distribution in this observable, and you can split this integral in 2 bits, one from 0 to some cut parameter, and since I'm going to use QT subtraction, I'm going to talk about QT cut, and then a region from a QT cut and above. And so if this observable has the property I just mentioned, then the region above the cut has already a resolved emission. And so now this is a process for, if you think about, for example, color singlet processes, now this region is going to be color singlet plus one additional jet. So then it's a lower order if we fix the order in perturbation theory of this object. And so you can use lower order techniques to deal with IR divergences. Now, of course, just like splitting this thing by itself, you have done nothing, because if you can calculate the region below the cut exactly, then you're basically able to calculate this object exactly. But the nice thing is that if you take this cut parameter pretty close to 0, then for this differential distribution in this region below the cut, you can actually use the leading power expansion in this observable, and this contains the singular bits that will contain all the most complicated IR divergences that pop up at that order. Of course, this introduces some approximation, some error that becomes smaller and smaller as you are able to take QT cut to 0. So now this has been an extremely successful program for color singlet, and even recently top processes at N3LO and Matrix and the group in Zurich, Massimiliano, has been like at the forefront of pushing that program. And of course, I want to mention also injectiness, which is interesting because it gives you the ability to tackle processes with jets in the final state, while Qt is more related to color singlet process with no jets in the final state, although there has been recent work in trying to extend Qt to processes with jets. Of course, the drawback is that it's very CPU intensive because you have to push this calculation of above the cut in a very singular limit, trying to basically, you're pushing that to more and more exposing the IR of your process. But I mean, there's been quite a lot of work in trying to make this more efficient by basically including more and more terms analytically in this region below the cut, and this goes under the name of calculating analytic perturbative power correction. There's been a lot of work in that in the last few years. Now, of course, this has been very powerful at N3LO, but the idea is how do we extend this to N3LO? Well, the idea is that the most complicated parts, as I said, are related to the region above below the cut. And so the idea is to look at what lies in the singular distribution, which is the one that enters in below the cut, where you want to have analytic control of this process or this differential distribution, and then we're going to use EFT methods in order to obtain these objects. So for Qt subtraction, the singular region is described by the TMD, so the transfer momentum dependent, or the transfer momentum distribution in PP at low Qt over Q. So the form in this singular limit of the cross section takes this form where there is a hard function that describes basically the virtual correction, and some collinear and soft object. Some of the collinear objects are the Qt-dependent beam function, the soft bits is the Qt-dependent soft function. We start looking perturbatively at this object. Let me call F some generic, just a placeholder for hard, beam, and soft. You can expand this object in perturbation theory, and you can get a form that has terms proportional to logs of the normalization scale, and then some characteristic scale of the either collinear, soft, or hard dynamic. And then there are boundary terms. So these boundary terms are the terms that are not logarithmically enhanced. And for N3LO slicing, we need the hard, beam, and soft function boundaries at N3LO, as you may imagine. So you basically need this object expanded in perturbation theory, also including the non-logarithmically enhanced terms at the order where you want to apply these slicing methods. And of course, the terms that are proportional to logs are kind of like easier in the sense that these have to be related to anomalous dimension or lower order results, beta function terms, and stuff like that. While the ones that are intrinsically new at a given order are these boundary values. So for the hard and the soft, the boundaries are just constant, literally color factor and numbers, zeta values in this case. And so they were known at N3LO since quite a long time. So for the hard function, these are basically is the form factor, known since 2010, and now we even know that at N3LO and N4LO, while the soft function was determined in 2016. So, however, the beam function boundaries are actually full function of the collinear splitting variables, so these in some sense are more complicated objects. So let me just spend some minutes in trying to understand what are these beam function objects. So if we think about a PDF at the end of the day is the object that enters in this in these hadronic predictions as a matrix element between QCD fields, can be quark or gluons, between proton states, and you have a measurement that picks up the longitudinal momentum fraction of the partons out of the proton. You can think about generalizing them with beam function, which is nothing more than a generalization of PDFs, wherein on top of the longitudinal momentum fraction constraint, you also measure an additional observable. So depending on the observable, you get different beam function. So you're going to hear about the Qt beam function and jettiness beam function. These are basically all related to the fact that you put different measurement here. So there is an important point. I just told you that you need this object at N3LO for doing N3LO slicing, but these are non-perturbative objects, right? These are generation of PDFs. PDFs are non-perturbative objects. So does that mean that you need like extraction of this differential object at N3LO? No, the point is that as long as your observable is perturbative, you can define an operator product expansion to match the beam function object onto the longitudinal PDFs. So the entire observable dependence is wrapped into perturbative calculable observable dependent matching kernel that is then convolved with the longitudinal PDFs. Of course, now you get on top of the observable dependence, you also get the variable that you have to convolve with the PDF. And so for the rest of the talk, when I talk about N3LO beam function, I actually mean N3LO order of the perturbative matching kernel. So a nice result that we have shown in this paper together with Marcus and Bernard is the fact you can relate these perturbative matching kernels to an expansion of a physical cross-section, differential partonic cross-section in the collinear limit. And so that allowed us to study this object from a more traditional fixed order point of view. So we went on, and to calculate the beam function at N3LO, we calculated the collinear expansion of the partonic cross-sections for Dralian and Hicks at N3LO. And since the two methods for doing the slicing procedure are n-jettiness and QT, as I said, we wanted to calculate both the n-jettiness and the QT beam function at N3LO. So we went through a kind of like more complicated object. We went to this double differential object where on top of the collinear splitting variable, you are also depending on both Qt and tau. So this is in some sense a double differential beam function. And out of that, we were able to obtain both the n-jettiness beam function at N3LO and the TMD PDF at N3LO, which is just another way of calling the Qt beam function. So just to give a little bit of context for how we obtain this object, so you need to calculate this partonic cross-section for Dralian and Hicks. This allows you to have access to both quark-initiated and glue-initiated processes at the LXC. This is still color singlet. And we want to be differential in this variable. So this is order 100,000 Feynman diagram calculation. This is done at the cross-section level, right? At the end of the day, these appear as the singular part of a cross-section object. We use the reverse unitarity to treat the phase space integrals. We didn't need to do that in full kinematics. We want to expose this beam function by going to the collinear limit. This, of course, allows you to do a power expansion that simplifies the dependence on at least one variable. We got more than like 1 million scalar integrals, and we went to a basis of master integrals via IBP identities. So, of course, for a cross-section level calculation, now you have to separate the different cases depending on the number of the emission in the final state. At N3LO, in principle, you have the purely virtual contribution, but these are completely encoded in the R function. Then you have the real double virtual. For them, we didn't actually need to use this machinery because these are known in full kinematics, and so you can just take from the amplitudes for x plus 1 jet at N3LO and crossing plus 1 jet at N3LO, and then expand. In that case, there is only one radiation, so it's pretty easy to do that procedure. The thing that were new and more complicated, as is always the case in these cross-section level objects, as you go to more and more complicated final state, it becomes more complicated. So actually, the loop correction tend to be the easier one. So the double real virtual, we got 170 collinear master integrals. In the triple real, we got 320. We derived system of differential equation for solving these master integrals. We have two non-trivial scales with algebraic dependence on the variables. And just to do a counting of the variables, basically there is the partonic center of mass or the invariant mass of the color singlet that just gives the overall scale dimension, and that one is trivial. And then you have these three variables. So naively, this would be three non-trivial scales, but one gets trivialized by the collinear expansion. So then you are left with two non-trivial scales in your problem. Of course, this is something that is beyond what we can do algorithmically, and we had some ways of putting the differential equation in a canonical form by constructing basically a basis of the log integrants by looking at the leading singularities on different cut surfaces. The boundaries for this system differential equation, thanks to the fact that we were fully differential in these variables, we can actually get them from fully differential soft integrals that have been calculated during, I mean, both in the calculation of the Higgs and Q-below cross-section, but also in later work by Falco, Bernard, and Claude. And there are also, like, you can get a lot of boundary condition just by constraining your cross-section to have the correct singular behavior in these additional variables. So, for example, these kind of constraints in the 2-2 at N3LO, which, I mean, Fabrizio has been pushing in the last few years, were enough to get all the boundaries, but we also needed some information from the soft integrals. So, having obtained this result was like unlocking the ability of doing a Qt subtraction at N3LO. So, the beam function was the last missing ingredient for both Qt subtraction and also Qt resummation at N3L prime. And since then, there have been a lot of phenomenological results that have been employing them. And so here we have the rapidity distribution in Dralian, the PT, the N3L prime, some fiducial cross-section in the Higgs with N3L prime resummation, and then other predictions that are coming from in Z and W production at N3L or N3LO. And just a mentioning of this paper that just came out like last week, also like this one was last year. So here is actually one of the few examples where people used the kind of like iterative slicing method. So this is an N3LO calculation using Qt subtraction at N3LO, but the part for the above, the piece for the above the cut term was actually used, obtained using one jettiness. So this is a slicing on top of a slicing. It's a very delicate and impressive work, and you know, the omega stability of this can be questioned, but it's pretty cool to see these things happening at this order. And then there are many more results. Recently, there's been a fast extraction from Atlas using PT distribution resummed to very high order, and so this has been like a pretty crucial ingredient. This has been okay. Oh, okay. 5 minutes? Okay, cool. Well, okay, then let me just go to the second half of my talk, which is how to go beyond N3LO, and this part of how we got the N4LO rapidity anomalous dimension. So this object is known in the literature with very different names. It's the Collins-Soper kernel, the collinear anomaly exponent. It's part of the B coefficient and the Sudakov exponent for PT resummation. It's also known as the TMD anomalous dimension. But in short, if you want to do anything with transverse momentum logs beyond next to leading log, you need this ingredient, willing or not. And as a matter of fact, so for the first two orders, this is the non-cusp part of this anomalous dimension vanishes. N3LO has been long for a long time, even though under a different name, and Massimiliano has actually been one that calculated that. That's basically the B2 coefficient. At N3LO, it's been determined in 2016 by Wai-Jing via some interesting bootstrap methods, and now we calculated that at N3LO and N4LO, and it's been another group that did that at the same time. So let me skip this detail and just show kind of like a picture of how we got this object. So this object is via brute force would be a fully differential N4LO calculation, so that's definitely way beyond what we can currently do. The nice thing is that there are a lot of relations that allow us to get this result out of objects that are known in the literature. So the for loop virtual anomalous dimension has been determined by Sven and collaborators. The for loop collinear anomalous dimension is part of the for loop calculation of the form factor. This is just the pole of the form factor, and there are some generalized Casimir scaling relations that allow you to get the for loop threshold anomalous dimension. On the other side, we need some ingredients coming from higher order epsilon, and we found a way of getting the 3-loop Qt soft function at higher order in epsilon from the inclusive one, which is a much easier object to calculate. And out of these two building blocks, there is an interesting conformal identity that relates the for loop repeated anomalous dimension to these two objects, and so out of that we were able to get this object. In the last -2 minutes, let me just say a little bit of how to do Fino with this ingredient. We now go to E plus E minus, just because we didn't have N3LO or like alpha s to the fourth splitting function. So to do a full N3LO resummation, we went to an observable that contains some TMD dynamics and that can be resummed using this anomalous dimension. So the example of this is the energy-energy correlator. Just measure the angles between pair of particles, and you weight that by energy to make it infrared and collinear safe. There is a lot of interest in this observable. It's kind of like a playground of QFT methods. There is alpha S extraction, precision test of QCD, but it also can be related to correlators in conformal field theories, and so there is a lot of crosstalk between N equals 4 and QCD in that. This object can also be studied with light ray, OPE, and there is an entire program that's going on by connecting some of the CFT techniques to QCD. This object also has an interesting structure because it has two singular limits, one where the particles are collinear, the other one where they're back-to-back. So this is the plot of actually the data from LEP. And although it seems kind of like symmetric, it is not. There's a structure, the singular structure in these two limits is quite different. There is a single logarithmic series in the small angle limit, and then a double logarithmic series at z going to 1. And we have factorization theorems at both ends. Before in kind of like standard QCD, there was like a leading log with jet calculus. Here it's up to next leading order by Massimiliano and collaborators, and now we push this thing to higher order in SCAT. So let me just focus in the back-to-back limit, where we have this Sudakov or double logarithmic series. This back-to-back region of the EC is really like a cross version of QT. And so there is a factorization theorem that kind of like looks similar to the one we've shown before. There is a Haar function, and there is a Qt-dependent object. This has a peculiar RG because it's a two-dimensional RG because we have these rapidity divergences. But nevertheless, this is just the resummed formula. You can solve this RG, and this is the analytically resummed formula, principal to all orders. And here, I mean, this is just a Fourier transform. There is the Haar function, the boundary function for the collinear and the soft object, and then there are scales that are elevated to some anomalous dimension. The rapidity anomalous dimension just mentioned before, it's part of this. So you can categorize the accuracy of this of the resummation for an observable just by looking at the perturbative order, which you know the ingredients that enter in the resummed result. So the higher you go in the perturbative order, the higher it is the resummation accuracy. So for N3LO resummation, this line, you need 3-loop boundaries, and so for the Haar function, this is just the form factors again. The EC jet function can actually, we calculated them, and there's basically a way of getting from the Qt beam function, you cross, you get the TMD fragmentation function, you take a moment of them, and you get the EC jet function. And in N3LO, and then the anomalous dimension with the for-loop collinear anomalous dimension, which again is something that is in the literature, the rapidity anomalous dimension that we determine, and then the 5-loop beta function, the 5-loop CASP, and then we used an approximation for the 5-loop CASP from Sven and collaborators. With that, we were able to produce, oops, this is the mouse, okay. this prediction at N3LO for this observable. This is the first time we do a summation for an event shape at this level of accuracy. We need a nice perturbative convergence of this result. So, well, more or less in time, let me conclude. So I introduced a motivation for why do we need to it's important to go to higher order in perturbative QCD, even beyond next link order. I discussed how to obtain TMD PDFs and jettiness beam function at N3LO. Presented the computation of the quark and gluon rapidity anomalous dimension for N3LO and see how ensure how you can use this to do Fino at N3LO for event shapes. So thank you.
Yes, of time for questions.
Thanks, Gherardo. I have a question and a curiosity. I start with the curiosity. In the factorization formula, the summation formula for this energy-energy correlation, is there no soft contribution, or is it like reabsorbed in the definition of the jet?
So yeah, so this is related. This is kind of like the same. You can phrase it, the same question also in PP, and what is the difference between the QT beam function and the TMD PDFs? And so this is actually, from my point of view, is just a different renormalization scheme dependence for the rapidity divergences. So you can either think of this object as including a square root of the soft function on each side, or I mean here actually I'm using a pure rapidity regulator, which is a regulator that we proposed in 2018. For this, actually the soft contribution are actually 0 at all orders, or if it's identical to the 3 level. So these are automatically into the collinear object, because basically you can get all the soft physics just as the soft limit of the collinear dynamics, and the rapid divergence cancel not between the soft and the collinear, but between different collinear objects, which is the reason why basically these objects are identical, with just the rapidity scale going to 1 minus the other rapidity scale. Yeah, that's it. But I mean, if you know what you're doing, you can do whatever you want.
They are the final state version of the TMDs. Okay, that's.
I mean, if you want to be technical, since you made the question, in the TMD you have a scale that is not canceling with the two objects. You just pull out Collins-Soper scale, and you actually assign the same value, and the rapid divergence cancel just by taking the product of everything from the get-go. While here, in some sense, you have this object, and this cancels between the two with literally opposite signs. While in the TMD they are identical, and you pull it out before.
Okay, thanks. The other question was, I think, it's slide 10. In the definition of the beam function, there was something that struck me. It was the hadronization the 9, that one. So, is it really, I mean, a linear correction in lambda QCD over the observable? Because then I will start to be worried, because if you go, I mean, this needs to be evaluated at a very small value of the observable, right?
Yes.
I mean,
so okay, there are two.
Can this become an order 100% effect, the non-perturbative correction?
That's a good question. I think there are like two like levels of answering this. So for slicing method, this is not an issue at all, because basically you are calculating, the idea is that you're still thinking that collinear factorization is valid, right? If you do the fixed order calculation for example, like the rapidity distribution in Dralian and N3LO, and you want to treat the singular region with QT slicing, right? Mm-hmm. What happens is that in order to get the full rapidity distribution, you also have to integrate over the QT equals 0 bin, right? Otherwise you don't get the correct result. But whatever non-perturbative information you are missing there is only going to give you non-perturbative correction to the rapidity distribution, right? So as long as you are happy calculating N3LO stuff without correction of lambda QCD over Q, then it's fine. Of course, this becomes trickier when you want to do differential distribution in the observable itself, and that, of course, is a different story, because then as you start pushing to lower and lower values of the observable, at some point you're just going to do non-perturbative part. The correction here is going to depend on what observable you use. And then there is the peculiar fact that even for example, for PT distributions, right, people use the, I can show you like this plot, right? I mean, you go to extremely low values, and you start thinking about this. The data here is at per mil, and you see that even the perturbative part is pretty small. And sure, I mean, there is some discrepancy here, but I would have naively expected the power correction here to be pretty small. Also, I mean, if you think about the fact that in Qt resummation or factorization, you always go into impact parameter space, then actually this power expansion is it's not in lambda QCD over tau, but it's in lambda QCD times BT.
Yeah, indeed, this non-perturbative thing gets spread out somehow. So.
Yes, and this one is, so there are different ways of doing what you can do. Of course, naively, you can just like parameterize this non-perturbative. You just use this as your leading power term, and then you have some model function for the region where BT becomes large. And this, for example, what is in Resbos and most of these in this Qt, even in Radish or all these codes that do these things. Of course, the thing becomes more subtle when you start to extract, for example, alpha S. And here, I think it's just like wrong to do it without a proper treatment of TMD PDFs, because now, I mean, it's already surprising you can describe PT distribution to such extreme low values of Qt without like a full non-perturbative Qt dependence. But as long as you have to do a plot, whatever, you have a bin or so, okay. Okay, maybe it's not the best thing. But if you start extracting parameters, then, I mean, I think this, and as a matter of fact, I mean, there is an entire community that is fitting non-perturbative beam function, and they are actually looking at these as not as a perturbative object, but just as a non-perturbative object that depends on KT. And then there is a nice, universality when you start crossing. So you can do, for example, extraction of beam function with low values of PT in PP, but also in semi-inclusive DIS as small Qt. You can, in principle, also do like so dihadron production at small Qt in plus, in minus. And in principle, these objects should be there's some kind of universality, and you have to extract. You could extract them. I mean, this is actually not like a surprising thing. It's the same way you're doing PDF extraction in DIS, and they use them in PP, and you also use PP data to constrain that. But in principle, you can do all of these also for TMDs, and I think it's necessary to do, to do this. But here is different, right? I mean, in this plot, I've integrated over the Qt equal to 0, and whatever I'm missing lambda QCD over Q or lambda QCD square, and these are not. It's not going to change. Just, you calculate these things just with the normal PDFs, and that's it.
Yeah, one quick comment and one question. So looking at what people do, probably you should put a caveat, handle with care these ingredients, because
yeah.
there is a, but okay. No, the question, I mean, I was curious, so a few days ago there was this talk by Prasanna, I think today he's not around, who presented this work with Stefano on the collinear function. So I was wondering if you have any comment on the way they define their objects with respect to what you do. And
this generating function with Pierre and so
no, I'm talking about this work on collinear functions where they compute basically, I mean, this by Dani and Catani. Probably you read it, no?
Okay. No, sorry.
No, you didn't read it. Okay, so then
I've missed it.
Okay. Then.
When was it?
It was 1 year ago.
Okay.
Okay, no problem. No, there was a talk by Prasanna here a few days ago. I was wondering if you had some comment. No. If you didn't read it, no problem.
I should have.
So I had sort of the same problem / question as Simone. So I am a bit surprised when in the context of something like this, which is sort of Drellian-like, you get linear power corrections. And I understand here you have an observable dependence, so I can cook up an observable, which is problematic. Do you know more about this? Like, is PT such an observable, I would expect quadratic. I mean,
yeah. No, I mean, yes. I mean, if you want, you can put a generic P as.
Okay.
Yeah. No, I mean, I wouldn't read too much into that. I think, I mean, yeah.
What I remember is that if instead of tau you use an invariant on an object like T or invariant mass, if you, instead of tau use T, like that is going to be lambda square, if I remember correctly.
Yes. But you know, I mean, it's then. I mean, I mean, correct. The thing is that then you start having, for example, in the soft function, things that are corrected by lambda QCD over the observable, but. No, I mean, I think here it's just like it's just like a slide to explain how you go from a non-perturbative object of the beam function to the perturbative matching kernel. And again, since you have like a generic observable, you can in principle have generic power correction.
Because of course it makes a big difference also for the stuff that you were mentioning. Like if you then want to determine something. Or make a concrete prediction for a measurement, if the corrections are lambda over some q squared, then
that is true. The thing is that I mean it's you still have like a dynamic. So for example, like in Qt, no matter what value you put, right, you are going to integrate over that in the Fourier transform. So it is true that it's dumped out by the Bessel function, but I think we have like, and I mean, there are like bigger issues that are neglected before like looking at. It is true. I mean, in general, they're gonna be quadratic. But for example, like there is the long. If you try to do in E plus E minus, right? So this object, the non-perturbative correction of this object would actually be part of the non-perturbative correction to the EC. But for some reason, in the literature, there is plenty of arguments that the EC has a correction that goes as lambda QCD over Q to the 0.27. I mean, even like bigger. And so this is, and then you get statements like, it's easier to extract alpha S in PP rather than E plus E minus because power corrections are bigger there, right? And I think, okay, probably it's. Yeah, I think especially if you are this is more general comment, if you are pushing to percent level, many of the arguments that are done for the non-perturbative part has to be actually now revised with a little bit of care. I mean, sometimes we have a talk tomorrow by Kirill exactly on that, but it's tough, right? I mean, you can have some model dependence, or you have like some approximation that don't know how to quantify it really, but this is especially for differential object is a very tricky point.
Exactly, because then one should also remember that it's always, even if it's squared, it's lambda over something squared, but something is always the smallest.
Yeah, exactly, it's not Q, right? So when it's quadratic, it's not lambda QCD over Q, which, okay, then of course I can throw away, but if it's lambda QCD over QT, and QT is 2GV, okay, it's squared, but whatever, right? I mean, it's not like a very small number.
Other questions?
Derivation of this rapidity anomalous dimension. When you combine various other ingredients to derive this, do you have some operator definition which allows you to relate this on a formal way, or is it just manipulating anomalous dimensions?
So let me give some details here. So I think the key equation is this one, and so it's basically saying that the rapidity anomalous dimension and the threshold anomalous dimension are identical or opposite depending on your convention in a conformal theory, and that also holds at the critical point of QCD, which you can say where QCD is conformal or not. That's more a different question. So this relation, there is the paper by Alexei that kind of like shows that by making just giving some operatorial definition of this object and making a conformal transformation that sense like the UV divergences of this object, which are related to the threshold one, to the rapidity, so the UV one to the IR one that are related to the rapidity, and so it's. I think it's a very nice finding, I wouldn't like bet my house on the framework of the proof, because for example they also prove it. He also proves it for the like not the dipole, but the higher point correlation, and this one is on less strong ground. I mean, you can have stuff going on. This one I think is going to hold. There is another kind of like proof in Wajing and Ian's paper, and basically you can think about looking at the EC in a conformal theory. In the back-to-back limit, you have a double logarithmic series with the double log is just given by the cusp, and then you have the single log, just basically the conformal version of this formula. So if you don't have running of the coupling, you can write this in a nicer form. And you start getting a relation between this collinear anomalous dimension and this rapidity anomalous dimension. And if you can prove that this anomalous dimension, the resulting single, the coefficient of the single log is the endpoint of Altarelli-Parisi, which is what you extracted in N3LO, then it basically, it is always in a conformal theory, then this means that you have this relation, because basically the other pieces cancel, and they cancel only if that thing is given. In the paper by Ian and Wajing, they just say, Krączewski gives us like this formula, and it says, there is a anomalous dimension, and this anomalous dimension is, and gives like 25 references where they put a lot of anomalous dimension, including the collinear anomalous dimension, that's in the planar limit. So if that is like a strong proof of that statement, maybe it's questionable, but let's say that it's still, I think it's still, I haven't found like a proof that really convinced me 100%, but I think it's a very, very strong conjecture, let's say, that is strong. Yeah.
Yeah, on a similar topic, I mean, there are different rapidity regulators, and it can be subtle in higher orders. Not even clear to me whether gauge invariance is always understood and so. So, to which rapidity regulator does it refer to, or do you just define it basically from the factorization formula that you wrote?
So that's a good point. But so one way that you can, and this is actually one of the challenges in trying to prove that more generically, is that I can give you these two objects are the ones that are related in this conformal point. But I mean, I just told you that even like this soft function in some rapidity regularization schemes is zero, right? I mean, so there is no, not even, so this is a technical challenge. The thing is that you can think about looking at the Q dependence of the entire cross-section once you factor out the half function, which is basically taking the like this factorization theorem. I can pull out the half function, and then I can ask the question, what is d by dq of this object? And I'm going to see that it's not just either like collinear anomalous dimension or the cusp, but there is something else, and this something else is the rapidity anomalous dimension. So if you want, you can define that if you just take the product of the entire thing, which is something that is pretty transparent in the CSS formula, right? Where it just like pull out, there is this lower energy object that is the TMD PDFs, and so that one, if you want, is it doesn't look at the way you split this renormalization scheme dependent object between collinear and soft bits, and it's just like a property of the entire cross section. Of course, yeah.
Just to come back to the question. So you basically treat it like a physical object, because you take this as a definition in a sense. You don't even need a rapidity regulator to calculate it, right?
Yeah.
But now coming from the other direction, right? If I want to, I define it from some operator or suggested. I introduce a rapidity regulator.
Yes.
And I calculate the dependence on the rapidity regulator scale. I would not automatically get this, right? If I take any of the rapidity regulators on the market. Well, so I mean, what is the true physical statement here?
I I mean, I don't know, this is like saying, if you, rather than using dimreg, you use some other regulator, you can get different objects, right? So
right, but
so
indeed, yeah. Of course, there's a factorization scheme depends. So this rapidity anomalous dimension, to which of the standard rapidity regulators does it refer? I mean, a few ones,
no.
right?
So this one, I mean, more or less, every rapidity regulator that is sensible is going to give you the same rapidity anomalous dimension. At most, you're going to get a factor of 2 different, right?
Okay, so what does sensible mean? So if I take the exponential regulator or the symmetric analytic or the other one, I always get the same thing? If I did this to 4 loops? No one has done this, right? But,
no one has done that, but you know, at the end, yes. I mean, it's you know, I mean, for example, like in this way where you, I mean, the number is going to be exactly the same. Also because I mean, modulo like just an overall factor. You're just not going to get like different you know, core factors or things in the anomalous dimension itself.
Yeah, I just wonder how to imagine, take the Chu, Rothstein, etc., this regulator. You know, it's very complicated. At 2 loops, you have to look at these web-type things in the exponent, right?
Yeah.
Now imagine doing this to 3 and 4 loop. Do you think it's understood with any of these practical regulators, and you would get this result?
I mean, then it depends how you define the counter term for the rapidity divergences, right? So that's
a trivial comment, but so the rapidity divergences are unphysical. Okay, so are just an artifact of the approximations that we do. So in the end, they have to cancel. So I mean, the fact that this object has to be independent on the way I regularize them, I think otherwise it's not. I mean, the result, the formula that you write would change depending on how you regularize the rapidity divergences.
Yeah, but that's the same for mu, right?
Which is not what I expect. So separately, the various ingredients of the formula can be defined by using different regulators. But at the end, I mean, the final formula has to be independent. Otherwise, it means that we are not understanding the physics, no? I mean,
on that I agree, but that's the same for mu, right? I mean, it's not that it's different, right? For mu,
it's the same
for the scale. I mean, you take d by d mu of the cross section, you need to get 0, and that's the same kind of like consistency condition that you have on the rapidity scale.
But in principle, it's the same. But since universally we agree on using the same regulator ms bar for mu, we don't think about it anymore. But in this case, we have different rapidity regulators which could be used for practical computations, and it's not yet clear that they should always give the same, right? So it's not yet on the same status as for mu. And so therefore, I was wondering how these kind of definitions relate to regulators that you'd actually put into Feynman integrals to compute things, right?
Yeah, I don't know if...
I will add to the confusion by, by noting that indeed you don't even if you don't use a formalism that has rapidity divergences, you still get the Collins-Soper kernel, which is very closely related. You get it the way Collins and Soper did, and the way, which would be like, I mean, in the language that I would use nowadays, an iconal jet made inclusive and integrated over the final state. Of course, that too, like Martin says, when I say these words, I imply that I use dimensional regularization and minimal subtraction.
I mean, it's a physical effect, right? The way you get that is different in QCD or in SCAT, because, you know, I mean, as soon as you start expanding, you get a different... But no, but, so, I mean, you calculated the rapidity anomalous dimension to 2 loops, right? And the fact that... So, that's fine, I mean, I don't care.
So, let me make, I mean, one comment. I mean, maybe I'm just my ignorance, but so in our way of presenting the resummation or doing these calculations, even in the case of take TT bar, okay, we don't need I mean, our ingredients are separately independent of the rapidity regulator. they are perfectly defined. They have no rapidity divergences. So in the end, the result, this rapidity, then in SCET you define a soft function which depends on the rapidity regulator, then you have, but in the end, the dependence on the rapidity regulator has to cancel out between the various ingredients. You can split it, and it can be more technically easier if you wish to use a certain regulator and then to carry on this dependence and then in the end to cancel it out at the end. But it has to cancel. I mean, at least this is my understanding. And then
I don't know. So I led the impression that there is no that the rapidity regulator is there or not. I mean, this this object. You know, like I mean, if you expand this, there is cancellation of mu dependence and cancellation of u, nu, call it whatever you want, and this is the physical cross section. There is not like much to say. Yeah. There are coefficients, you know, you can write everything is in the exponent in terms of some logs, and this is just like number at the end of the day, right? I mean, literally, the rapidity anomalous dimension is, at for loops, is this, right? There is nobody tells you that, right? Now you can take these, you can add other pieces, call it B2, you can call B3 or B4, and whatever, but I mean, it's there, right? It's not that you can cook up a way of not getting that. And as a matter of easy or not easy, I mean, at N3LO and N4LO, these have been determined in SCET, right? So everything that's been done after next to next leading log for Qt has done first in SCET and then in other methods. So of course, maybe even if you like introduce these new divergences that were not there in QCD, maybe still gives you like a better handle technically of extracting this object that in QCD is there, because at the end of the day, SCET is just like the infrared limit of QCD. It's not something different, right? In a different, right? So, and so, you know, I can...
So again, talking about things that know more, know better. So take again heavy quark. So Chacon has computed the soft function for heavy quark production, for Qt, and his result is different from my one. His result depends on the regulator he has chosen. Okay. My result is a rapidity regulator independent because it's strictly defined in a way that it does not need any rapidity regulator. So, I mean, then you can, of course,
the physical cross-section is the same.
The physical cross-section is the same because his rapidity regulator dependence will cancel out with the beam functions and with all the rest. So that's perfectly fine. It's a different way of organizing the calculation.
Yeah. What is it that you are calling B? And you said that there is the B of the Sudakov.
I mean, if, you know, like in standard CSS, you can write just some hard times e to the a times log square plus b. Yes, and you know, it's part of.
Okay. Any other questions? No, everybody is happy? Okay, so let's thank Gherardo again. Thank you very much.